Hello. I checked the video and it seems to be the volume was decent. It was at half volume and I was hearing myself. I cranked it up and it was loud. So I hope the other student found a way to figure out what was going wrong from maybe her end. I hope if anybody is having trouble hearing me now, please speak up. And I noticed something else in the other video. I don't know how to edit your face out of the videos. I saw somebody's face occur in the top right corner of the screen under mine, and I can't do anything about that. I hope there's no problem there. But we're going to continue with this exercise here. The mirror image of carbon 5, which was R, is now S. And the mirror image of carbon 3, which was R, is now S. And I don't have to check these facts. I just need to know the mirror image of an R is always an S. Now, exercise 3, I want to draw three R5S. Now, there's many ways you can do it. You could start from
Doctor,
scratch.
I don't think
Hello.
you're sharing your screen. I can't see it personally. I'm not sure about.
Oh, yeah. And I think if you're not seeing my screen, everybody's not. And you're right. I didn't do that. Yeah. All right, guys, we're back. Okay. All I did while you were gone was I didn't have 3R written. I didn't have 3S written. But the first thing I drew, I put the label on there and I put that there. And then I came up with this new question here. I copy pasted and I edited the 5 to S. And I have a strategy for you that should be able to get you there. Let's see. I'm going to do it. It might take a second. I'm going to copy everything I got here. I got this thing here. If I had thought ahead, I could have done this a little better. Yeah, we got this. And I just trying to show you. And that iodine's not going to be there. Part of my strategy to get us there is the single switch. So those seem to be part of each other. All right, well, as you can tell, I am copying what I did on stereo center 3 because I want stereo center 3 the same. The name has it 3R and it's still 3R. And this is the beauty of the single switch about to come up. If you have an R stereo center and you do just one switch, like an iodine for an isopropyl, what used to be R will now be S. So I'm putting the iodine on the dash where the isopropyl used to be, and the isopropyl on that normal bond where the iodine used to be. And look at that, without having to do any thinking or figuring out, I've already finished that job. Isn't that nice? And you know my fourth question probably before I ask it. Oh, can I get the name? I got everything except for one parenthesis. Not bad. And part 4, I want to draw. This time, though, I want 3. Let's say I want the mirror image of 3R5S, which would be 3S5R. Eraser, eraser. 3S, 5R. And when I'm done, I will have all possible isomers that have that name at the end. And guess what? This is a hidden way of asking you what's the draw the enantiomer of this molecule. Look, the enantiomer has both stereocenters different. And let's see. technically I'll be drawing the mirror image when I'm done. But these two, notice is the mirror image of this. The iodine will be towards the mirror this time. I know my labels aren't right. I will fix them. The iodine is towards the mirror. The isopropyl is away. And these labels are both wrong. The mirror image of 5S is 5R. And the mirror image of 3R is 3S. And then part 5. Some of you saw these as you were skipping these questions on old exams. Label each pair of isomers. Each pair, we're going to get a new word very soon too, of isomers as enantiomers. And for this question, you can use the short form E, or here's a new word, which we'll define on our next page, diastereomers, D. And we'll do those labels here. The mirror image of these two, and we'll just do it like this in red. The mirror image are called enantiomers. And they have both stereocenters changed. Okay. It's like hands and feet. This is a one-handed guy and a one-footed guy. So say 3 is a hand and 5 is a foot. The mirror image of a right foot is a left foot, and the mirror image of a right hand is a left hand. And same down here, mirror image of a right foot is a left foot, and a mirror image of, I think you got the idea. But what about this pair here, where one of the stereocenters is changed, but the other did not? The mirror image, this is not a mirror image at all. This is the same stereocenter. And this stereocenter is different. You can't say they're enantiomers. So they must be the other one. Diastereomers. Same story between these two here. Where the 5 stereocenter changed and the 3 stayed the same. Same story down here. You have to be careful. The 3 here is on the left side of the molecule. It's the opposite of the 3 here, but the 5 here is the same as the 5 here. I know they're not drawn the same, but they're both are, which means they are the same. It's just like, this is my right hand. This is still my right hand. Okay? Doesn't matter how you draw it. It's the right hand because it's got the parts in the right place. So this is D. And doing the other comparison, I'll do it in blue. That'd be the second one and the third one. The S on 3 is different. The S on 5 is the same. So these will be the quick points at the end of this question. You don't even know what the question looks like yet. But it's an 18-point question, which we will do from the very beginning. In the form, you'll see it on the test. And I hope everybody does well on this question. So let's do it. And it'll start like this. Part A. Draw all isomers of, let's do one that's a little different. 1 4 dibromo methyl 1 4 no just one this time 1 let's do tert heptyl cyclooctane. And we should have tert is italics. And that's part A. And then B, label each stereocenter. Remember, stereocenter is a short form, stereocenter, as R or S. Each stereocenter, the word itself, is a short form for stereogenic center. And then C, compare each pair of molecules like we did at the end. Each pair of molecules as enantiomers. Short form E will save you a little time. Or diastereomers, which we haven't defined yet. I think you have a sense of it, though, before we even define it. In short form D. And you'll see that on lots of exams, either test 1 for semesters where we got all the way through chapter 3 on the first test, or it shows up in test 2 if it didn't show up in test 1. And let's move this over and do our definition of diastereomer above it. Diastereomers. If it ends with mer, it's some kind of isomer, right? Isomers with the same name where some is the magic word of the stereocenters are the same, where some of the stereocenters are the same and some are different. So just go back quickly to our previous example. They all had the same name at the end. In these two, they were both different, so that doesn't fit the definition of diastereomer. When everything's different, that's called enantiomers. But you look at this name here and this third name, the 3 stayed the same and the 5 changed. That is going to be diastereomers. Same for these two. Oh, these two are, no, they're enantiomers. Different. But if you compare 1 and 3, this was 2, or 2 and 3, the 3 changed, the 5 stayed the same. Or 2 and 4, the 3 stayed the same and 5 changed. Then you see diastereomers. They're easy to spot. And the consequences of this chemically are profound. I'll do a brief introduction. Enantiomers, they'll have almost every possible physical property you can think of that's identical to each other. Okay? Boiling points, melting points, densities, all exactly the same. Then you go to diastereomers, and they're all different. So they have different chemical behavior in every way. But enantiomers, they have almost the same behavior. But in biochemistry and in chemistry where other handed molecules interact, as you can imagine, like a hand interacting with a glove, then you need the right fit for the reaction to proceed as it should. So it's a very important property, handedness. And also being enantiomers or diastereomers is also very important too. We'll talk about that probably first thing, well, maybe at the end of today. We'll see how this goes. So diastereomers, isomers with the same name, where some of the stereocenters are the same and some are different. So we're going to start by drawing cyclooctane. We'll draw it once very nicely. And then I'll copy paste it. Let's see if I can do this. This won't be fair for you because you can't do this on a test. It's not the best octagon. It's not terrible either. All right. Okay, we decide carbon 1 and 3. 4, sorry. And we put a dibromomethylene. Now don't be confused by this. There's a group called a dibromomethyl group. That is not what this question's looking for. If it said like 1-dibromomethyl, then you have a methyl with 2 bromines on it. This says 1,4 means 2 groups that are identical. One's on 1, one's on 4. They're called bromomethyl groups. The di has to do with the fact that there are 2 numbers. Okay, a bromomethyl group looks like this. Methyl with a bromo. Methyl has a bromo. On 4, same story. On carbon 1, there's also a tert heptyl. Strategy for any tert is to start with the chicken foot. There is tert butyl. How many more carbons do you need for heptyl? 3. Pick one of the feet and make it have 3 more carbons in a row. 1, 2, 3. Verify you've got to 7. 1, 2, 3, 4, 5, 6, 7. So there you go. You got 0 points so far. Wow. This is not a nomenclature question. This is all about stereocenters. Please, carbon 4. This is stereocenter. I need to see all 4 things. Carbon 4 has an H. Now we're going to use our strategy to figure out if these groups are wedges or dashes or what. And I'm going to do priorities. You have to do all the good hard work on the first molecule. And then we have strategies that quickly get us to molecules 2, 3, and 4. We're just going to follow that guided exercise. I'll remind you, in the guided exercise, the next molecule I drew after I finished this molecule was the enantiomer by drawing its mirror image. And then the third molecule, I drew the first molecule again and did a single switch on one stereocenter. Trust me, that's what we did. And then the fourth molecule, I drew the enantiomer of the third. And I was done, except for the comparisons. So moving back up here, we have to do our stereocenters. We have to do a real good job because a mistake on the first one translates to a mistake on every single stereocenter. And my pen is not letting me do what I want to do. A carbon with a bromine is number 1. Red might be a bad choice since I got red on there already. A carbon with 3 bonds to carbon is 2. Which of these CH2s is going to have a higher priority? Well, when it's just CH2s for a while, then you can talk about branching. CH2, CH2, C with a branch. CH2, CH2, C with no branch. And hey, you're in charge of wedges and dashes now, right? You don't want to do more work than you have to, right? So if you put the 4 on a dash and just tell me what the stereo center is, you don't have to worry about switches or anything. Let's put the 4 on a dash, shall we? Choose purple. Make sure it goes all the way. And a wedge on an adjacent bond. It can be either this bond or this bond. I find it easier when it's outside the ring. It's personal preference. Okay. And now if you connect 1 and 2 and 3 with the 4 already on a dash, it's counterclockwise. You're going to put a label on there and you're going to get a half point for each label. The first labels are the hardest. Everything else follows after that. They're the easy ones. Counterclockwise, S. Go down to the bottom stereo center. Guess which group's the 4? You got it. It's the H. And we'll go hot pink. The 1 is a C with a BR. The 2 is a C that hits a branch earlier than a straight chain with no branches. Put the 4 on a dash. Make your life easy. You don't have to. If you don't put it on a dash, you're going to have to do a double switch to check your own stereo center. Why are you doing that to yourself? I get asked this question a lot, even after what I just said right now. Does the number 4 have to be on a dash? I say no, it never has to be on a dash. It sure is easy to determine if it's R or S when it's on a dash, but it does not have to be on a dash. It can be on any of the 4 bonds. There's nothing wrong about putting 4 anywhere you want. Okay, so now this is also S. Put a label on there. Okay, next molecule is easy. I'm going to draw the mirror image. You don't have to show me the mirror. I'm not going to give you a point for drawing the mirror. You're going to draw the cyclooctane. Let's see. I didn't draw a very symmetric cyclooctane. It's very strange. That's not bad, is it? I think we can figure it out. All right, close to the mirror. The 1 is up top right. Hey. 1. No, I moved it down, but that's okay. 2, 3, 4. How do you draw this bond? It's towards the mirror, almost horizontal, just a hair down. I had mine totally horizontal, no big deal. And the H looks like it is straight down on a dash. That is a lazy dash. I don't like it. And on stereo center 1, this thing's slightly away from the mirror. And please don't freak out if I draw this in the same direction as before. Is this a stereo center up here? Answer no. So does it matter which way the BR points? Answer also no. Yes, you can draw it to the left up towards the mirror if you want. It's fine. It's the tetrahedron that needs to be the mirror image, right? Okay, describe this wedge relative to the mirror. It's away from the mirror, a little bit up. It's got the tert heptal on it. Okay. And where was the dash? It was from 1 to 8. You don't have to put the 8 on there. What's the mirror image of an S stereo center? R stereo center. What's the mirror image of this S stereo center? R stereo center. So in A, you're getting 2 points each for the drawing. In B, 0.5 points each stereo center. My course policy is generally 3/4 of a point for each stereo center. So you're getting undervalued on your first stereocenters and overvalued for the easy ones. Notice I didn't do any work to get this R except see the mirror image. And C we'll do later, where we're supposed to compare 1 point each comparison. 6 quick points. Okay. I can cut to the chase. Your strategy for the third molecule was to copy the first molecule, pick a stereocenter, do a single switch on it. So you want it to be stereocenter. What did I do a single switch on last time? Was it the 5 or the 3? I can't even remember. It was the 5. I'll do it on the 1 this time, just to show you it doesn't matter which one you do a single switch on. I went the wrong way. Here we go. I'll do a single switch on the 1. So I'm going to put on the wedge here, the CH2Br. Top left, CH2Br on a wedge. Dash here still. Didn't do switch there. And the tert. The tert will be on this bond here. There you go. That's a single switch on an S. Guess what it's going to be? An R. It's a good strategy. You can use whatever strategy you come up with, but this one works for me. I'm going to, don't you dare do a single switch on the other stereo center. Do you know what's going to happen to you? Let me describe briefly what happens to you and how much time you are wasting. If you also do a single switch on an S stereo center, you will be drawing an R stereo center. You will just have drawn this molecule from a different perspective. You get no points for the same molecule twice. None. You get no points for comparing because you're already going to compare this to this. So do not do single switches on both stereo centers. That's just another way of drawing an enantiomers. And you already drew enantiomers here. Okay. So keep the other stereo center exactly the same. Do not change anything. Did not change that stereo center. It is still S. And my strategy to finish it off was to draw the mirror image of the third molecule right here. And we'll go monochromatic here, all blue. And we have a dash going here. We have the wedge away from the mirror here to the CH2Br. We have a normal tert towards the mirror slightly. Don't worry if you draw the methyls left or right. That's not a stereo center up there. I don't care how you draw those bonds. And guess what the mirror image of the orange R is? It's the orange S. Mirror image of the purple S. It's purple R. And then I'm going to take a break here, but I will put the next question on the screen. And I want you to think about it. I'm going to try to edit this one. And it will not take long, I hope. I'm going to change the name ever so slightly. 1,4-dibromo 1, 4 dash di tert haptyl cyclooctane. It's the only change I made. And now you're going to see after we discuss, when we return, that there's going to be one less isomer here. Well, we didn't finish the previous one. Just realized we only did one comparison. We threw away the 5 easiest points on the test. We got 1 out of 6. When both stereocenters are opposites, what do you call them? Enantiomers. When one's the same and the other's changed, some are different, some are the same, D. Some are different, some are the same, D. The S stayed the same, the R changed. And in the middle, same story. D, color change. D, 6 comparisons, 6 points. Almost threw them away by stopping the segment. We're going to pick up with this question here. Almost the same name, except I've got 2 tert butyl groups instead of just the one. I will see you on the other side.